Welcome folks to Lecture 5. Lecture 5 is a very exciting and important lecture as well, and the title of today's lecture is the frequency response of amplifiers. Basically, the amplifier response depends on the frequency content of the input signal. And in order for us to understand how the amplifier behaves, we have to review some basic concepts first. In order for us to understand the frequency response of amplifiers, we must understand the behavior of the single time constant RC circuit. The circuit is shown here. We have a voltage source connected to a resistor, which is connected to a capacitor as shown. This is very fundamental circuit. You should have mastered it in early courses. If not, this is your last chance. Make sure you pay attention and make sure you understand it. We will use this circuit to design amplifiers in CMOS technology. You see, we are talking about state-of-the-art analog IC design. What we're going to look at is we are looking at the frequency response in CMOS circuits based on single time constant RC circuit. We will have an understanding for the analog CMOS circuits based on our understanding of the RC circuit. This is great. This simple circuit advances the technology. Let's look at it in more details. So one of the things we will notice is that the voltage source VI and the resistor R are basically the Thevenin equivalent circuit at the input stage. So if you have an amplifier, the amplifier has an input stage. This input stage can be a previous amplifier or a previous module, or it can be the input signal coming in from the antenna in the case of a wireless circuit, for example. So input stage can be either input signal or it can be the output of the previous stage in your system or in your circuit. By any means, we can use Thevenin theorem to simplify that input stage into a voltage source and an input resistance. Also, the capacitor C is basically the parasitic capacitance of the transistor, the layout, and so on. So basically what we're saying is this capacitance can be created by the equivalent capacitance of the transistor at the input or the equivalent capacitance of the output of the previous stage or the interconnect, which means the wires that connect the previous stage to this stage. Now we can say that the output voltage Vout can be evaluated using the voltage divider. Right? Because you have two impedances in series connected to VI, then Vout is nothing but the voltage divider. So we can say that Vout will equal to the output impedance over the sum of these two impedances times the input voltage. This is a basic voltage divider concept. So it will be Vout of S will equal to 1 over SC over R plus 1 over SC times VI of S. Over here we are using the impedance of the capacitor to be 1 over SC, so we are using the S domain, right? Frequency domain and S domain are kind of related. Now by multiplying SC on the top and the bottom, we can see that V out of S will equal to 1 over 1 plus S times RC times VI. And if I take the output over the input ratio, which is V out of S over VI of S, this is basically the gain of the circuit A of S, and that is will equal to 1 over 1 plus SRC. And that is very exciting. So now what you do is say that we know what's the gain of this particular circuit in the frequency domain. It's nothing but a voltage divider. We calculated it. We can convert this circuit from the S domain to the omega domain basically by replacing S with j omega. Remember that if we say S will equal to j omega, then we transform the circuit from the S domain to the frequency domain. Basically, the S domain is the general case that is used to solve for the circuit using the differential equations. The S domain is the easiest way to do it, while the phasor domain or the frequency domain is applied to a pure sinusoidal signal. So you can move from a general case, which is the S domain, to a pure sinusoidal signal, basically by replacing S equals to j omega. That's all what we did. By replacing s equals to j omega, you transform the circuit from the general case, which is the Laplace domain case, to the phasor domain or the frequency domain, where we are using the pure sinusoidal signal. That's all what's into it, really. So now what we do, we say that A of j omega, replace s with j omega, will equal to 1 over 1 plus j omega RC. Wherever you have s, just replace it with j omega. But this is a complex function. What do you mean by a complex function? It uses complex value or complex variable kind of function. Then it has a magnitude and a phase, right? So the magnitude of the gain is basically the absolute value of A of j omega. This will equal to the magnitude of the top, which is 1, over the magnitude of the bottom, which is the square root of the real part squared plus the imaginary part squared. So this will be the square root of 1 plus omega RC quantity squared. If we plot magnitude as a function of frequencies for this particular function, it's very interesting. You will have a flat response, that what we call as the DC response, because when omega equal to 0, you have a gain of 1, which in dB is 0 dB actually, so it's 0 dB. And then as the frequency increase, you start to see that the denominator term become more dominating. That means the gain start to drop. So if we will look at the response in dB, it will fairly be flat until we hit the corner frequency, which is the 1 over RC value. So when omega equal to 1 over RC, we start to see a sharp drop. And that's what you see here, is we have a flat line that represents the DC gain until we hit the 1 over RC frequency, and then the gain will start to drop linearly in dB. Right? So this is something we know from previous courses, and the corner frequency is very important to us. It's a function of R and C. Remember that. So basically what this circuit says is that the voltage at the capacitor, or the voltage at the output of this circuit, is flat until I hit the corner frequency, then will start to rapidly drop. The signal will die at the output if it has a high frequency content. That's all what we're saying here. Of course, you can also do the phase of the circuit. So the phase of the gain or the output voltage is basically the phase of the top, which is 0 because this is a real value, minus the phase of the bottom. And the phase of the bottom can be evaluated to be the tangent inverse of the imaginary part, which is omega RC, over the real part, which is 1. So you will have minus the tangent inverse of omega RC. If you plot this function, what you will have is roughly 0 degrees until a decade before that corner frequency. A decade before omega RC, then you start to see the phase will drop linearly almost until a decade after that corner frequency, which is 1 over omega RC. What's interesting is that the phase of the output voltage or the gain at the corner frequency is minus 45 degrees, and the phase at very, very high frequency is minus 90 degrees. So this plot here represents the phase of the transfer function. So basically it's not only the signal will drop as the frequency increase, but also the phase will shift toward 90 degrees as the frequency increase. So far we said that the RC circuit is a function of frequency, and the signal at the output of the RC circuit will drop as the frequency increase. That's all what we said. So we would expect that the signal to be weaker at the output of the RC circuit, or basically across the capacitor, as we increase the frequency. Right? So this is very important observation. In fact, that's why the signal of the amplifier dies at high frequency. What we are interested in now is the frequency response of amplifiers based on the RC circuit model. So what we're going to do now is we will look at the amplifier. So this is an amplifier, and we will say that the gain of the amplifier is A0, and it has Vx as the input of the amplifier, and it has Vout as the output of the amplifier. This is an amplifier. And what we're going to do, we will say that the input of the amplifier contains RC circuit. So basically, you will have Vi, which is the input signal, connected in series with R, connected in series with C, which are connected to Vx, and Vx becomes the input of the amplifier. This is a model. In fact, the whole thing is an amplifier. You have an input signal going into the amplifier. This input signal has an equivalent Thevenin resistance called R. It represents the equivalent Thevenin circuit of the input stage. And then we have a capacitance that is parasitic. It's there, we don't like it, it's just parasitic. Part of technology, you're going to have this capacitance there. When we implement and develop the amplifier, we will have that capacitance. So we can say that the resistor and the voltage source are the Thevenin equivalent of the input. And the capacitance C is the equivalent parasitic capacitance of the transistor, the interconnect, and the wires, and also the output of the previous stage. So now what is interesting is we know the following. For this particular circuit, we know that the output voltage as a function of frequency, so we can say that V out of j omega will equal to the gain of the amplifier, which is A0 times Vx of j omega times the input of the amplifier as a function of frequency. In CMOS technology, this is very important. The input stage of the amplifier has infinite impedance, so you can see that all of the current flowing through the resistor will flow through the capacitor. This is in CMOS technology, right? So now we can assume that R and C are in series, then Vx can be evaluated using the voltage divider, right? So we can say that Vx of j omega will equal to 1 over 1 plus j omega RC times Vi. Now because we solved for Vx, we can solve for Vout. Then Vout of j omega will equal to A0 over 1 plus j omega RC times Vi of j omega, or we can say that the output over the input, or the gain of the overall amplifier, is basically V out of j omega over Vi of j omega will equal to A of j omega. This is the overall gain of the amplifier here for this circuit, and that will equal to A0 over 1 plus j omega RC. So this is very exciting. Let's go back and review what we said. All what we said is if you have an RC circuit by itself, then the voltage across the capacitor will drop as the frequency increase. And then we said that if we will amplify the voltage across the capacitor using CMOS amplifier, this signal V of X will be amplified through the amplifier. And that signal Vx is a function of frequency, then Vout will also be a function of frequency. Now keep in mind that the actual amplifier inside the IC chip contains the capacitor and the ideal amplifier, because the capacitance is parasitic. Remember that inside the IC circuit, and we're going to find an equivalent capacitance at the input. We will show you that in this lecture, how to evaluate the input equivalent capacitance. Another important observation is not only the input stage that has equivalent capacitance, also the output stage has an equivalent capacitance. So the output also has equivalent resistance and output capacitance. And we're going to show it to you here. So here is the input stage of the circuit. You have Vi connected to Ri, which is connected to C1. And then here we have Vx, which is connected to the amplifier with a gain A0. And then at the output, we will have a resistance, we will call it R2, that is connected to a capacitance, we're going to call it C2, which is connected to the output. Then the gain of this amplifier has two RC circuits, one at the input and one at the output. Then the gain will look like this. A of j omega will equal to A0, which is the gain of the amplifier without any frequency, or the DC gain if you want to call it, divided by 1 plus j omega R1 C1, which is the RC effect of the input stage, times 1 plus j omega R2 C2, which is the effect of the output stage. And this is very bad. The high frequency element will drop twice, one at the input stage and one at the output stage. And that means the high frequency drops very rapidly as a function of frequency. So if we plot the magnitude of the gain for this particular circuit, we will see that you will start with A0 at dB, which is the gain at dB at very low frequency, and you will stay flat until you hit the first corner frequency, and then you will drop with 20 dB per decade until you hit the second corner frequency, and then you drop at another 20 dB per decade. Usually, it's not always the case, but usually for a single stage amplifier like this one, the input stage is more dominating than the output stage, which means that the earlier 3 dB frequency occurs because of the input stage. And the reason is the input stage usually has very high input impedance, while the output stage has very low output impedance. If C1 and C2 are in order of magnitude of each other, then it's obvious that the input stage has higher RC time constant, which means lower 3 dB frequency. So the input stage usually in a single stage amplifier has the lower 3 dB frequency. So far what we said now is how is the frequency response behaves for the amplifier if there is a single time constant circuit at the input and a single time constant circuit at the output. And this is a practical circuit, and you will see that we will use the circuit to develop the frequency response of the amplifiers that we have learned so far. We are starting here by saying that the frequency response of the amplifier affected by the RC time constant. We have RC circuit at the input and RC circuit at the output, and they both affect the frequency response of the amplifier. That's all what we're saying. And this is the transfer function for the gain, or the frequency response of the gain. It has two poles, or two 3 dB frequencies, one for the first RC circuit and the other one for the second RC circuit. That's all what we're saying. Alright, the next topic we're going to talk about is Miller's theorem. Miller's theorem is also another important topic to understand the frequency response of the amplifier. Why do we use Miller's theorem? If this is your amplifier, for example, it is possible that C of F, which we call the feedback capacitance, that is connected from the output back to the input or from the input to the output. It is possible that the parasitic capacitance is located across the amplifier from the output to the input. This particular scenario occurs frequently inside the amplifiers. So let's show you an example in a common source configuration. For example, let's assume that we have this transistor, we're going to call it M1, which is connected in a common source configuration, which means we have an input, which means that we have an input voltage connected to a resistance connected to the gate of this transistor, and then we have RD is connected at the drain, connected to VDD, and finally the source is grounded. Now we can draw the small signal model, especially the pi model. So let's look at the pi model. We know that we're going to have VI connected to R1, and that is the gate, and then we're going to have the drain, which has the current source connected in parallel with RO, that is small RO, the output impedance across the transistor. And finally we have RD connected from the drain to ground, because VDD is grounded when it comes to the small AC signal. And the source, of course, is grounded, so everything is grounded. Now this particular model is the intermediate frequency model. To include the high frequencies, we have to add the capacitances of the transistor. Then we're going to add CGS, which is the gate source capacitance, to the small signal model, and we will add CDS, which is the capacitance from the drain to the source of the transistor, and finally we will add CGD, which is the capacitance from the gate to the drain. Now remember that this node is the output and this node is the input of the amplifier. Then this CGD is the shunt capacitance between the output and the input, right? So this scenario occurs very frequently. In fact, that the common source amplifier is a function of frequency because of these capacitances. And let's see how we're going to deal with such a circuit. How would we use Miller's theorem to solve for this circuit? Well, the first thing we have to say is why we would use Miller's theorem. What would Miller's theorem do to the circuit? Well, basically Miller's theorem simplifies the circuit analysis by approximating the location of the poles of the circuit. So the question now, what is Miller's theorem? The answer is very simple. Let's assume we have two nodes, node X and node Y, where there is an impedance between these two nodes. So the way I think of it is node X is the input of the amplifier and node Y is the output of the amplifier, and then we have this capacitance connected from the output to the input. Or we're going to call it, in a general case, that we have an impedance Z between X and Y, between the input and the output of the amplifier. So Miller's theorem in general says that's what we have. Now, I wanted you also to pay attention that this impedance can be expressed in terms of the admittance of the circuit, which is 1 over Z. So it can be impedance or it can be admittance, it's the same thing. Now, we would like to define the gain. So let the gain between the two nodes to be defined as AV will equal to VY over VX, which means that Vy is the output and Vx is the input of this amplifier or of this circuit. Then the network has an equivalent network as shown here. What's the equivalent network of this circuit? Well, what we'll do is we will say that this impedance Z at node X, at the input, we will see it as Z1. So basically node X will only see Z1 going to ground. And node Y will only see Z2 going to ground. Right? Because the intuition says I don't care what goes on beyond node X, all what I see is one equivalent impedance at node X will go to ground, and I will call it Z1. And the same thing at node Y. If I will look back into node Y, all what I will see is an impedance that is going to ground. Basically, it says that there is a current will go to ground from node Y through Z2. Now, the question is, what's Z1 and what's Z2? Well, Z1 is basically will equal to Z, which is the impedance between the two nodes, over 1 minus AV. So this is very interesting because if AV is negative, then minus AV becomes a positive quantity, right? And similar thing happens to Z2. Z2 will equal to Z over 1 minus 1 over AV. So if AV is negative, then it comes 1 plus 1 over the magnitude of AV. This equation can be expressed in terms of the admittance because 1 over Z is the admittance. So basically what you have is Y1 will equal to Y times 1 minus AV, and Y2 will equal to Y minus 1 over AV. So the admittances become much bigger at the input if the gain is negative and large value, and it becomes roughly the same at output if the gain is negative and very large value. So what we are saying is if gain is negative, the Miller admittance at the input Y1 becomes much bigger than the shunted admittance Y, and the output admittance Y2 is similar in value to the shunted admittance Y. Keep in mind that we assume in here the gain is negative large value. Let's just show you example how we can use it. Let's assume that we have this amplifier, and this amplifier has a magnitude minus A, minus 100, minus 200, minus 500, minus A. And then we have a shunted capacitance that goes from the output to the input. We're going to call it CF. Now, what we would like to do is we would like to find the Miller's equivalent capacitance at the input and the output. So that's what we are after. So basically, the circuit should look like this. By Miller's effect, you should have C1 at the input, then you have the amplifier with a gain of minus A, then you have C2 at the output. Right? That's by Miller's effect, that's what we have. And now we can say that Y1 will equal to S times C1. That's the admittance at the input for C1. And that is basically by Miller's theorem, says that will equal to Y, which is the shunt admittance, times 1 minus AV. So now let's substitute for the values. Then say Y1, which equals to S times CF times 1 plus A. Then we say Y1, which equals to S times C1, and that would equal to S times CF times 1 plus A. Then what we do is we cancel the S's from both sides of the equation, and then we say C1, the equivalent capacitance at the input, will equal to CF, which is the shunt capacitance, times 1 plus A. Remember that we made it a plus here because minus the minus A is plus A. Then what we have now is the input capacitance is much bigger in value by roughly the amount of the gain. You see, that is when the gain is negative. Now, similar scenario will happen at the output. Similarly, the output capacitance due to the Miller effect is given as Y2 is equal to S times C2. That's the definition of the admittance, which equals to, by Miller's theorem, Y times 1 minus 1 over AV. And when we substitute for AV, this will equal to S times CF times 1 plus 1 over AV. So it is obvious that the S's will cancel out, and then what we have is C2 will equal to CF times 1 plus 1 over AV. So this is very exciting. Let's give you numeric values just to give you an understanding of the quantity. Now let's assume that CF is 10 picofarad and the gain minus A will equal to minus 100. So minus A is minus 100, or A equals to 100. The gain is minus 100, but A is 100. Then by Miller's theorem, C1 will equal to CF times 1 plus A. So when you plug in the values, you will have 10 picofarad times 1 plus 100. That gives you 1.01 nanofarad. So the magnitude of the capacitance becomes 101 times bigger than CF. Now let's look what happens to C2. C2 will equal to CF times 1 plus 1 over A, which is basically CF times 1.01, and that is 10.1 picofarad. Roughly, the output capacitance is the same as CF. Right, it's close to 10 picofarad. So what happens is the input capacitance becomes very large while the output capacitance is the same as CF. Right, so that is important. So let's state that, very important note, the input capacitance becomes much bigger than the feedback capacitance when the amplifier has negative gain. So far, we have presented Miller's theorem, and we said that Miller's theorem converts a shunted capacitor, the amplifier, from the input to the output into two capacitors. One capacitor is located at the input, while the other capacitor is located at the output. Then we said if the gain of the amplifier is negative, then the input capacitance is much larger than the output capacitance. So the question now is why Miller's effect is important. Why are we discussing the Miller's effect? Remember, this course is about what? It's about analog CMOS VLSI design, right? So then why are we studying this theorem? The answer is very trivial. MOSFET transistor has a shunt capacitance from the gate to the drain. We call it CGD. So CGD is a shunt capacitance from the gate to the drain. Well, the Miller's effect of the shunted capacitor dramatically affects the frequency response of the amplifier. Then the frequency response of the amplifier can be approximated using two RC circuits, one at the input and one at the output of the amplifier. So that's why we are studying Miller's theorem in this particular course, because MOSFET transistors have shunted capacitor from the gate to the drain. This shunted capacitor experiences the Miller's effect, which means that you're going to have a capacitance at the gate and a capacitance at the drain, and the capacitance at the gate will be much bigger than the capacitance at the drain. So what we will do next is we will show you that we can evaluate the frequency response using Miller's theorem, and we will do that for the common source amplifier. So pay attention to it, because this is very important technique. It's supposed to be a quick technique to come up with the frequency response of the amplifier. So let's look at the small signal model one more time for the common source amplifier. We have V1 is connected in series with R1. This is basically the input Thevenin equivalent of the previous stage. And then we are connecting this to capacitance from the gate to the source. We're going to call it CGS. And then we have another capacitance from the gate to the drain. We're going to call it CGD. And at the drain we have this current source, which is GM times VGS, which is connected in parallel with RO. That's the small signal RO, which is connected in parallel with RD. And then there is that capacitance from the drain to the source. We're going to call it CDS. And keep in mind that we are neglecting the body effect here. That means the gate and the source are connected together. So this is the circuit. It's the common source amplifier, and we are interested in evaluating the frequency response of the system using the approximation of Miller's theorem. It is obvious that the shunted capacitor CGD can be converted into two Miller capacitors. One will be at the input and one will be at the output. But before we evaluate the Miller capacitance, the amplifier's gain is needed. What is the gain of the amplifier, and how would we evaluate it? So to evaluate the gain of the amplifier, we will use a valid approximation, which is to use the mid-frequency gain. So basically we will evaluate the mid-frequency gain to come up with the gain of the amplifier. At the mid-frequency, the capacitors are open circuit, because these capacitors are very small in value. That means they only exist for high frequencies. So if we will look at the intermediate frequency or the low frequency, these capacitors will be open circuit. Then the circuit will look like this. We will have V1 connected to R1, then CGS is open circuit and CGD is open circuit, and the source is grounded, of course. Then we will go to the drain, and the drain we will have the current source connected in parallel with RO, connected in parallel with RD, and CDS is open circuit. So all the capacitors are open circuit. Then we end up with the conventional pi model that we are used to. Once we draw the intermediate frequency equivalent circuit, we can evaluate the gain of this amplifier. We know the gain of the amplifier A is equal to minus GM times RD in parallel with RO. Now we evaluate C1 and C2, which are the Miller capacitances at the input and output. Then C1 is given as C1 will equal to CGD, that's the shunted capacitance from the output to the input, times 1 plus the gain, which is 1 plus GM times RD in parallel with RO. Now keep in mind that the gain is much bigger than 1, that's usually the case. Then C1 will be much bigger than CGD, where C2, which is the capacitance at the output, is given as C2 will equal to CGD, which is the shunted capacitance, times 1 plus 1 over the gain, which is 1 over GM times RD in parallel with RO. And that is approximately CG. And then we can approximate the circuit right away. So we can say that what C1 is and what C2 is by inspection if we are familiar with the circuit. And now we know that C1 is much bigger than C2. Then the new equivalent circuit will look like this. I will have V1 connected in series with R1. This is the Thevenin input equivalent circuit of the amplifier. Then we have CGS, which is the input capacitance from the gate to the source, and that is in parallel with C1 because C1 goes from the gate to ground, right? And then CGD have disappeared because we found the Miller equivalent capacitances for it. And at the drain we have the current source, which is GMVGS, in parallel with RO, in parallel with RD, and then here we have the capacitance CDS, and we also have C2, which is the output Miller capacitance. Let's state this note one more time. C1 is large in value, and it is parallel with CGS, whereas C2 is small in value, and it is in parallel with CDS. We know that capacitors in parallel are added up, so I can combine CGS and C1 to one equivalent capacitance, and I can combine CDS and C2 into one equivalent capacitance. Then the equivalent circuit will look like this. I have V1 connected in series with R1 connected in series with CI, and then I have GMVGS connected in parallel with RO, connected in parallel with RD, connected in parallel with CO. Now we can obtain the transfer function or the frequency response very easily. The transfer function of the amplifier is approximated using 2 poles and the DC gain. So let's show you how we can do that. We are obtaining the frequency response using Miller's theorem. The first pole of the amplifier, we're going to call it omega P1, will equal to 1 over R1 CI. 1 over R1 times CI is the first pole, whereas the second pole of the system, omega P2, will equal to 1 over RO CO. Whereas RO is the parallel combination of a small RO in parallel with RD, and CI will equal to C1 plus CGS, and CO will equal to CDS plus C2. Then the overall gain is given as A of S will equal to minus GM times RO in parallel with RD. This is basically the intermediate gain, or what we call the DC gain of the circuit, divided by 1 plus S over omega P1 times 1 plus S over omega P2. So note that what we did here is using Miller's theorem. That's why Miller's theorem is powerful. What we did is we said that the overall gain will have the intermediate frequency gain, which is GM RO in parallel with RD, and then we have two poles, one pole at the input, one pole at the output, and the input pole is omega P1 and the output pole is omega P2. Then we approximated the transfer function. Note that if you will set S equals 0, you end up with the DC gain. If we plot the magnitude of body plot for this amplifier, we will start with the DC gain, which is flat until we hit the first pole, and then we will drop at 20 dB per decade until we hit the second pole, and then we will drop by another 20 dB per decade. So you will have total of 40 dB per decade after the second pole. Now the phase of the gain starts with 0 degrees and then will drop to 90 degrees a decade after the first pole, and will drop to another 90 degrees a decade after the second pole. So the maximum phase shift for this amplifier is minus 180 degrees at very high frequency. One disadvantage of using Miller's theorem is that it ignores the effect of a zero located at very high frequency. There is a zero created by a shunted capacitor. Miller's theorem ignores that zero. On the other hand, the locations of the poles are very accurate, that Miller's approximation continues to be favored by most engineers. So most of the designers will use Miller's approximation to locate the poles of the amplifier, even though it ignores that zero at very high frequency. And remember that we are really interested in the frequency response because we wanted to make sure that the phase margin is within tolerable region such that the amplifier is stable when we use it in a feedback. This concept is studied in controls, so make sure that when you use the feedback amplifier that the op-amp is stable if you have a phase margin roughly is selected to be anywhere between 60 to 40 degrees, which means that you are 60 degrees away from the 180 degrees when the amplifier reaches unity gain or 0 dB. So this concept is studied in controls and it is touched on in some of the electronics courses. But the frequency response is very important, not only because it will tell us what's the response of the amplifier as a function of frequency, but it will also be crucial to the stability of the amplifier in feedback systems. And the stability of the amplifier means that the amplifier is working and is not oscillating. The signal is amplified. Otherwise it oscillates, and we're going to dedicate a chapter for oscillators and how we can create a circuit that will oscillate later on in this course. But it is crucial for us to understand the frequency response of the system, not just because the gain attenuate as the frequency increase, but also wanted to make sure that the amplifier is stable. Alright, now we are interested in the frequency response of amplifiers. And we are looking at a special amplifier right now, which is a common source amplifier. In the previous slide, we have shown you how we can come up with the frequency response of the common source amplifier using Miller's theorem. And that frequency response using Miller's theorem, we said that is approximated. Now we are interested in evaluating the frequency response of the common source amplifier using the derivation of the transfer function. So basically we will derive the transfer function or the frequency response of the common source amplifier. And we can do that using any of the circuit analysis techniques we have learned in earlier courses, such as nodal analysis, mesh analysis, but you will be able to derive the frequency response using any of the techniques that we have learned in circuit analysis. So let's go back to the small signal model for the common source amplifier. So what we have over here is the voltage source VI connected in series with the Thevenin resistance R1, and we say that at the gate of the transistor there is a capacitance called CGS connected to ground because the source is grounded, and there is another capacitance connected to the drain, we call it CGD. And then we also have at the drain we have the current source, which is GMVGS, which is connected in parallel with RO, which is connected in parallel with RD, that is the load resistance, and we have the capacitance CDB, that is the capacitance from the drain to the body, right, CDB. And what we will do now is we will derive the frequency response of this amplifier, of the common source amplifier, using nodal analysis. So we will go to the output node. So here is the output node, and we will sum currents leaving the output node to be 0. That's the way I write the nodal equations. I sum the currents leaving, so I don't have to worry about the directions of the currents, whether they are going in or out of the node. And I stress this in the early circuit courses. I might deviate from most of the circuit authors, but the reason I like to sum the currents leaving because it is systematic, and also when it comes to analyzing complex circuits it becomes just very intuitive. For me it is much easier. I come to the node, I sum the currents leaving, the node equals 0. By any means, when we sum the currents leaving the node, I will have current leaving the output, and the first thing I will look at is the current leaving the current source, and that will equal to GM times VG, because VS is 0, so I will say VGS is the same as VG, so it is GM times VG, plus the current leaving the output resistance, and we know that these two resistors are in parallel, so we will say plus Vout over RD in parallel with RO, plus the current leaving the capacitance at the drain. The current leaving the capacitance is the admittance times the voltage, so it will be S times CDB times Vout, plus the current leaving shunt capacitance, and because this is a capacitance, so we're going to say that it is the admittance of that capacitance times the voltage across this capacitance from the output to the gate. So it is S times CGD times Vout minus VG, and that should equal to 0. So this equation is very interesting. What you have here is two unknowns. You have VG is not known and you have Vout is not known. So what I will do now is I will express VG in terms of Vout. So we will solve for VG in terms of Vout, and after some algebra this will yield to VG equals to minus Vout times S times CGD plus CDB plus 1 over RD divided by GM minus S times CGD. So we end up summing the current at the output, and we simplified the equation using some algebra such that we can express VG in terms of Vout. So now what I will do is I will sum the currents leaving the node, the gate. So at the gate node we will have the current leaving the input resistance, which is Vout minus Vi over Rs. Rs is the same as R1, it's the source resistance. So we will say Vout minus Vi over Rs plus the current leaving the gate to the source capacitance, which is S times CGS times Vg, plus the current leaving shunted capacitance, and this current will be from the gate to the output, so it will be plus S times CGE times Vg minus Vout equals 0. So now in this particular equation we have three unknowns. We have Vi, Vg and Vout. But from the previous equation we can substitute for Vg in terms of Vout by substituting for Vg in this equation, and we will be able to come up with the gain expression. Then the gain equation will look like this: A V of S, which is the gain, will equal to V out over V in of S. So that's the gain as a function of S, as a function of frequency. This will equal to, it's a rational function, at the top is S times CGD minus GM times RD over RS times RD times CP S squared plus RS times 1 plus GM times RD times CGD plus RS times CGS plus RD times CGD plus CDB, the whole thing multiplied by S plus 1. So what's interesting here is the denominator is a second order transfer function, right? So keep that thought with you. But also we have to say where is CP, the parallel capacitance, is given to be CP equals to CGS times CGD plus CGS times CDB plus CGD times CDB. As I said, the denominator of the rational function of the gain is a second order polynomial. Then we have two poles. So the first pole we're going to call omega P1 will equal to 1 over RS times 1 plus GMRD times CGD plus RS times CGS plus RD times CGD plus CDB. And the second pole is omega P2 will equal to, this is another rational function, is RS times 1 plus GM times RD times CGD plus RS times CGS plus RD times CGD plus CDB over RS times RD times CGS times CGD plus CGS times CDB plus CGD times CDB. It's basically the parallel capacitance. What is interesting is also there is a zero on the right half plane which is located at very high frequency. Omega Z1, which is the zero, is equal to GM over CGD. So that zero is located on the right half plane. Now, very interesting that these equations look a little bit scary, but they are trivials. So let's give you some notes about this transfer function, and we're going to compare it to the Miller theorem that we have used. So here is the notes. The first thing we're going to say that Miller theorem provides a very good approximation to the location of the poles. If you evaluate omega P1 and omega P2 using Miller theorem or using this accurate transfer function derivation, you will come up with very close values. The location of the poles are very close in values. However, Miller's theorem fails to give value for the zero. And that's something we stated earlier on in the previous slide. We said that Miller's theorem cannot or ignores the effect of the zero. Well, the zero is important. You cannot totally ignore it because there are situations where the zero got to be accounted for, especially in ultra-wideband amplifiers. In ultra-wideband amplifiers, we are interested in very, very high frequencies. So in ultra-wideband amplifiers and low-power amplifiers. So what that means is GM is very small, and we would like to have very high bandwidth, right? So these two requirements are important. In low-power amplifiers, remember GM is a function of the bias and current, so you have to make sure that the bias and current very small for low-power amplifiers. And we are interested in very large bandwidth. If you combine these two conditions, that zero may lower the stability constraints, which means that it is making the amplifier less stable. So you got to watch for the stability condition in ultra-wide bandwidth amplifiers and low power amplifiers, because GM is small and the frequency response needed is very large. So this zero will add phase shift to the system that it might make the phase margin less desired. So watch out for it. This is a topic, as we said earlier, studied in control, so make sure that this condition is fulfilled. Another thing we are interested in when it comes to the frequency response is we have to look at the input impedance of the amplifier. So the input impedance of the common source amplifier is also going to be a function of frequency. Let's look at the amplifier here and let's see how is this implemented. So we're going to start with the transistor M1. This transistor M1 has a gate to source capacitance, and it has a gate to drain capacitance, and it also has a drain to body capacitance. And you can calculate these capacitances once you know the geometric shape of the transistor, the size of the W and L, and the process parameters to implement the transistor. So evaluating these capacitances can be easily obtained once you know the geometric structure of the device and once you know the process parameters to implement this transistor. Then we also have RS coming to the gate and RD going to VDD, and at the same time we have the source connected to ground. So we are interested in the input impedance of the amplifier, which is what's looking into the gate of the transistor, right? Keep in mind that these capacitors are parasitics. They are inside the transistor. We do not connect these capacitors in the outside of the transistor. They are inside the transistor. They are parasitics. We don't like them, but they are there. So when you look into the gate, we've been saying so far is the impedance to the gate is infinite. Well, because of these capacitances, now there will be input impedance. We are interested in this input impedance. To do that, we will define the input impedance to be Z1 in parallel with the impedance of the gate to source capacitance. So we will say it will equal to Z1 in parallel with Z of CGS, which is nothing but Z1 in parallel with 1 over S times CGS. So basically Z1 is looking into the gate of the transistor. So we are interested in the input impedance of the amplifier, which is what's looking into the gate of the transistor. Keep in mind that these capacitors are parasitics. They are inside the transistor. We do not connect these capacitors in the outside of the transistor. They are inside the transistor. They are parasitics. We don't like them, but they are there. So basically Z1 is looking into the transistor after the gate to source capacitance. So now we will solve for Z1 by applying Vx and solving for Ix. We are applying a test voltage and solving for the test current. Basically, that's one of the techniques that we can solve for the equivalent impedance at the input. Now we will solve for Z1 by applying Vx and solving for Ix. Now we are going to skip the steps, but basically when you solve for Z1, which is Vx over Ix, what you will end up with is 1 plus Rd times S times CGD plus CDB over S times CGD plus 1 plus GM times RD plus S times RD times CDB. And remember one more time that Zi is Z1 in parallel with 1 over S times CGS. So the input impedance is not infinity, but it is a function of frequency. This is very important observation because we used to say that the input impedance to the common source amplifier is infinite, but it's not, because of the following: because of the shunt capacitances and the capacitance from the gate to ground. These capacitances will have leakage at very high frequency. In fact, that when the frequency approaches infinity, this input impedance becomes zero. which makes sense to us because we also said that the gain will become 0 when omega goes to infinity. Remember from body plot of the gain, we said that the gain will drop to 0 or very negative dB, which means 0. And that is because one of the reasons is the input impedance becomes small. Another reason the gain drops to 0 as omega goes to infinity is the output impedance also becomes 0. So the output impedance is 0 and the input impedance is 0, then the gain drops twice as fast. Well, so far the circuit is not practical because remember we are about analog VLSI inside the chip. How would we develop an analog circuit? So that's not the way we implement common source amplifiers on the IC chip. So we have to use active load. So in the practical common source amplifier, what we do is if RD is replaced by an active load, which means BMOS transistor, then the circuit will look like this. We will have M1 and M2 connected together, and then we have the input from RS. Now keep in mind that M2 will be biased, whether we're going to use a current source to bias V bias like we did in the differential amplifier, or you can bias it using any other technique where we said that M2 will be biased using V bias, and then there is all these capacitors around. Let's look at the capacitances. We have a capacitance for M1 that will go from the gate to the source, we call it CGS1, and there is a capacitance will go from the gate to the drain of M1, so we call it CGD1, and there is a capacitance will go from the drain to the body of M1, we call it CDB1. Then there is also capacitance will go from the gate to the drain of M2, we call it CGD2, and we have a capacitance will go from the gate to the source of M2, so we call it CGS2, and then we have a capacitance will go from the drain to the body of M2, we call it CDB2. As you can see, we have these 6 dominant capacitances, and we can evaluate each of these capacitances as we said earlier once you get the process parameters and the geometric shape of the transistor. The geometric shape of the transistor is a function of the design. We get the gain of the amplifier by looking at the geometric shape of the transistors, and we get the capacitance values of the amplifiers by knowing the geometric shape or size of the transistors. So the geometric size of the transistor determines the gain and determines the frequency response because it tells you the magnitude of the capacitances. By any means, what's interesting is for this particular circuit is if we look at the equivalent circuit, we will have similar equivalent circuit is obtained if the load is the active BMOS transistor. So we will have similar equivalent circuit like the one we discussed before, right? It's the common source amplifier. What we will have is VI connected to R1, which then we will have CGS1 connected from the gate to the source of M1, and the source is grounded, and then we have CGD1 which is connected from the gate to the drain of M1, and then we have GM1 VGS which is connected to RO1, and we said that the equivalent resistance seen from the drain across M2 is RO2, but also we will look at the equivalent capacitance. We're going to call it C2, which is looking at the drain. So at the output we will look at equivalent capacitance will go from the drain to ground. If you are at the drain, you will see CGD2, the capacitance from the gate to the drain of D2, because the gate going to be biased, which means 0 AC, so the AC signal will be connected to ground from the drain to the gate, and then we're gonna see another capacitance will be from the drain to the body of M1, and another capacitance will go from the drain to the body of M2. So basically the equivalent capacitance C2 at the output is equal to CGD2 plus CDB1 plus CDB2. In summary, the equivalent circuit of this practical circuit is very similar to the common source amplifier. The only difference is how to obtain the value of these capacitances, but the equivalent circuit, the small signal equivalent circuit, is the same for the common source amplifier and the common source amplifier with active load. They have the same equivalent circuit. Basically, we will have similar transfer function, and also the CGD1 experiences the Miller's effect. Then we can express the transfer function as follows. A of S, which is the gain as a function of S or as a function of frequency, will equal to minus GM times RO in parallel with RD. This is basically the intermediate frequency gain or the DC gain, times 1 minus S over omega Z1 over 1 plus S over omega P1 times 1 plus S over omega P2. So basically we have a 0 and 2 poles, and now let us tell you what each one is. We can approximate the first pole, which is omega P1, to be 1 over R1 times CI, and omega P2 to equal to approximately is equal to 1 over RO times CO, and omega Z1 approximately will equal to GM over CGD1, where C out is basically C2 plus CGD1, and CI is basically CGS1 plus 1 plus GM1 times RO times CGD1. So that's the Miller's effect. And RO is basically small RO1 in parallel with small RO2. So far, this was a very important circuit we have discussed. We said that what's the frequency response of the common source amplifier, and we used nodal analysis to derive the transfer function. When we use the nodal analysis, we come up with two equations, and then we eliminated one of the unknowns because we have two equations. We used one equation to eliminate one of the unknowns, and then we end up with expressing V out in terms of VI, and we came up with the gain equation. We end up realizing that there is a 0 located in the right half plane and 2 poles, and the location of the 2 poles are very close to the Miller theorem that we have obtained. Then we also said that the input impedance of this amplifier is a function of frequency because of the capacitances at the input. That means the input impedance drops as we increase the frequency, which explains why the gain drops as we increase the frequency. Then we also said that when we implement the circuit for IC design, we have to use active load. And when we use the active load, which is a BMOS transistor for the load, then we end up with the same equivalent circuit. The only difference was how to evaluate the values for the capacitances and RO. But we came up with a second order transfer function, and have a 0 also located on the right half plane. And now we are ready to study more amplifiers using similar techniques. We are also interested in the frequency response of the source follower, which is the common drain amplifier. Now recall that the common drain amplifier says that we have VI is going through RS, which is the input impedance that is connected into the transistor M1, and the output signal will be measured at the source. So it's a common drain amplifier because the drain is connected to VDD, which is grounded, and then we have the input signal at the gate and the output signal at the source. Now the transistor is biased using a current source called I, and the load we have output impedance called CL. CL is large in value because this kind of amplifier usually physically is connected at the output stage of the amplifier. That means the load capacitance is large because it is the output capacitance. Usually this capacitance is set by the standard or the manufacturing process. For example, if the output is connected to an I/O pin, then depending on the technology, CL will be specified to be less than some maximum value. You have to meet the specification for CL. So for now, we will say that CL is a dominant large capacitance because this particular amplifier is usually used at the output stage, which means that this amplifier usually is connected to the output I/O pin of the IC chip. So, sometimes you have to take this output into an I/O block because you have electrostatic discharge and so forth to protect the chip from damage. So basically, CL is the capacitance, and the electrostatic discharge circuit usually has large capacitance, and that is directly connected to the output pin of the IC chip. So CL is large in value, and it's specified by the technology and the design we use in. It is part of the specification of your IC chip. So now we are interested in evaluating the gain for the common drain amplifier. The first thing I'm going to do over here is to draw the small signal equivalent circuit. Keep in mind that this equivalent circuit here is simplified model. If you wanted to look into a complex model for accurate answer, you have to depend on the computer simulation. Basically, the analysis is very tedious to do by hand. But what we will do here is we look at the shortcut approximations in order for us to understand the behavior of these amplifiers. So the small signal models we are using in this lecture are approximations, and the reason we do that is because we wanted to come up with approximated values which are very close to the physical values that you get when you implement the IC chip. So you have to really depend on computer simulations to get the right answers. Even then, your answers will be approximated to the physical values. And these things are acquired through experience. You have to look at the hand calculations, go to the computer, do the simulation, compare and see where the discrepancies are, then go back and implement it on the chip, and then look at the results and see where the discrepancies are. So this is the first cut. This is understanding the circuit. You still have to go and do it using computer simulations where you can use the simulation to get the right answer or to get more accurate answer and then or more accurate results. Then you take it to the fabrication and you implement the IC chip. So over here it's an approximation. We have to stress this one more time. So we're going to look at the simple model, the AC model for this amplifier. We will use the pi model. So I will have VI, which is the input signal, connected to RS. And then we have CGS, which is the capacitance from the gate to the source, and that is connected to CGD, which is the capacitance from the source to the drain. And at the source we have CL, which is the load capacitance. The source is the output, which is V out. And then from the drain to the source we have the current source, GM times VGS, and we have RO is in parallel with it, and the drain is grounded. So because the drain is grounded, we can reflect a couple of things. Because the drain is grounded, we can redraw this small signal circuit a little bit different where it is easier to understand. So what we're going to have now is we will have that gate to drain capacitor is actually connected from the gate to ground, so you can reflect that capacitor to ground. So we will have VI connected in series with RS, and then we have CGD connected from the gate to ground. Then from the gate to the source we have the capacitor, and then what I will do is I will reflect the impedance of the current source at the source, so this will become as a transconductance or as a resistance that will equal to 1 over GM. And small RO is connected from the source to the drain, but the drain is grounded, so it is the same as saying that it is connected from the source to ground. So that's what we have here, is small RO is connected from the source to ground. And then we have CL connected from the source or the output to ground as well. So the circuit look a little bit simple and easy, but we have made few assumptions here. The first assumption we have made is we are ignoring the body effect. So we do not count for the body effect when we calculate the gain. We will use it for the input impedance, but we will not use it for the gain. So now we are interested in evaluating the gain. The way we're going to do that is we will sum KCL at the output node first. So let's sum the KCL at the output node. So we will say the current going in will equal to the current going out of the node. So to write the KCL equation, we have to also label the node at the top to be VG and the node at the bottom to be Vout. And when we sum the currents at this node, we will come up with this equation. We will say that VG times S times GS plus GM. So that is basically is the sum of the currents going into the node will equal to Vout times SCL plus GM plus SCGS plus 1 over RO, and that equates the currents leaving the node. So basically, when you write the KCL equation, you will come up with this equation. Now we can express VG in terms of Vout. So VG will equal to S times CL plus GM plus S times CGS plus 1 over RO divided by GM plus S times CGS times Vout. So that is easy to do. So what we did is we summed the current at the output such that we can express VG in terms of Vout. Actually, we can even approximate this equation a little bit more, assuming that if the frequency is moderate in magnitude, then S times CL is bigger than any of these values, bigger than GM, because GM usually is small in value, and then SGS is much smaller than SCL because CL is much bigger than CGS. 1 over RO will be very small value. So the dominating value will be S times CL. So we can say that VG is approximately will equal to S times CL over GM plus S times CGS. Now keep in mind that both values of the denominator are kind of small. When you combine them together, you still have a small value. So you have a dominant effect on them. That's why you cannot ignore them. We only minimize the numerator terms. Times Vout, that gives you VG in terms of Vout. So we simplified the equation. Now what I will do is I will sum the voltages at the input. So also by applying KVL at the input, we get the following. We say that VI, which is the input, will equal to RS times the current flowing through it. So the current flowing through this resistor, which is RS, is basically the current flowing through CGD and the current flowing through CGS. So the current flowing through CGD is basically VG times CGD. So we say RS times VG times SCGD. And the current flowing through CGS is VG minus Vout, which is the voltage across this capacitor, times the admittance, which is times S times CGS. So this is basically the voltage across RS is RS times the current flowing through it, plus VG, which is the voltage at the gate. I already know what's VG in terms of Vout, so I can do the substitution for VG in terms of Vout, and then I can solve for Vout over VI. Now, by substituting for VG and solving for the transfer function or the gain, we have Vout over VI of S will equal to GM plus CGS times S divided by RS times CGS times CL plus CGS times CGD plus CG times CL times S squared plus GM times RS times CGD plus CL plus CGS times S plus GM. What is interesting here is the transfer function is a second order with two poles. The two poles are far apart. This is very interesting. The two poles are far apart, which means that one will have a major impact in the transfer function. The other one can be neglected, right? So the dominating pole, the first pole, which we're going to call omega 1 is approximately will equal to GM over GM times RS times CGD plus CL plus CGS. If we set Rs equals to 0, then omega 1 is approximately will equal to Gm over Cl plus Cgs. Now, what is interesting here is that the dominating pole is a function of the bias and current, because Gm is a function of the bias and current. So the dominating pole is a function of the bias and current. The larger Gm, the larger the dominating pole. That means we push it apart. It's a function of the load capacitance Cl. So the bigger the capacitance, the sooner the pole will occur. And the same thing with Cgs between the gate and the source. If it is bigger, that means that the dominating pole is very small, and that is bad. That means the bandwidth of the amplifier is small. You want to make sure that the dominating pole as far as possible. Now what you do is, in order for you to increase the bias and current, most of the time what do? You increase W, you reduce L, right? So that's one of the ways you can do it, is by increasing W, reducing L. You get larger current, you get larger Gm. But if you increase W, you increase the capacitance. So there is a trade-off. One more time, make sure that the frequency response of the amplifier as large as possible while we maintain the stability condition. The next thing we are interested in here is the input impedance of this source follower amplifier, of the common drain amplifier. And the input impedance is evaluated basically using a test source Vx. So what we're going to do is, if you will look at the circuit, we have Vx connected to the transistor M1, and over here we will make the capacitance Cgs to be more dominating, and then we will include the body effect, so we will see 1 over GMB at the bottom, and then we have the load capacitance across the output, and the drain is connected to VDD. Basically, if you draw the small signal model, it will look kind of simple here. We have Vx connected to the capacitance, which is Cgs, and then at the source, which is the output, we have 1 over Gm and we have Cl, and from the drain to the source we have GM-VGS. We neglected the effect of small RO because small RO going to be in parallel with 1 over GMB. So the load resistance in parallel with 1 over GMB in parallel with 1 over GM is basically 1 over GMB. So over here we made few approximations because we are interested at the input impedance. We said that 1 over GMB will have a major effect because the resistance of 1 over GMB is smaller than 1 over GM, and it is smaller than 1 over RO. So basically what we do is we ignore CGD because it is small, and we include the body effect, which is 1 over GMB because it is the smallest resistance, smaller than 1 over GM and smaller than RO. That means it's the more dominating term. That's why that's the way the equivalent circuit look like. Now what we're going to do is we would like to evaluate the input impedance basically by using KVL. So by KVL we will say that Vx, which is the input voltage, will equal to the current times the impedance of that capacitor. So it will be Ix, which is the current, over S times Cgs. The current time the impedance is the voltage across the capacitor, plus the current going to the output, and the output will have 1 over GMB in parallel with CL, and the total current going through the output will be the current coming from the gate plus the current coming from the drain. The current coming from the gate is Ix, while the current coming from the drain is GM times VGS, whereas VGS is basically Ix over S times GS. So now what we have is the current going to the load, going to the output, is Ix plus GMIX over S times CGS. This is multiplied by output impedance, which is 1 over GMB in parallel with 1 over SCL. Now it's clear that Ix term is included in every part in the right half side of the equation. So now we can say that Zi, the input impedance, is Vx over Ix. By factoring Ix and dividing it in both sides of the equations, what we will have is 1 over SCGS plus 1 plus GM over SGS times 1 over GMB in parallel with 1 over SCL. So at low frequencies, we can say that the input impedance will equal to approximately 1 over S times CGS plus 1 plus GM over GMB plus 1 over GMB. And at very high frequencies, we can say that the input impedance is given as approximately 1 over S times CGS plus 1 over S times CL plus GM over S squared times CGS times CL. Now finally we are interested in the output impedance. What happens to the output impedance at the circuit? So what we are interested in is, ignoring CL, what will be the output impedance looking into the source. Remember, to evaluate the output impedance you have to apply V-test and calculate I-test at the output. So here is the pi model after you kill all the input sources. So the input source is 0, and then we will have RS connected to the gate, and then from the gate to the source we have CGS, and we applied Vx at the output, and we are interested in Ix at the input. And then from the drain to the source we have the current source GM VGS. Over here we ignored RO for simplicity. Keep in mind that the drain is also grounded. So this circuit is easy to calculate, and when we evaluate Z out, which is Vx over Ix, we end up with this approximation. It will equal to Rs times S times CGS plus 1 over GM plus S times CGS. So in order for us to minimize the output impedance, we have to increase GM and CGS. So what we did so far, we said that the gain will be a function of frequency, the input impedance will be a function of frequency, and the output impedance will be a function of frequency. And that makes sense, because if the gain changes as a function of frequency, so does the input impedance and the output impedance. That's what we are saying here. The change in the input impedance and the output impedance as a function of frequency causes the change in the gain as a function of frequencies. We are also interested in the frequency response of the common gate amplifier. The common gate amplifier will look like this. We will have the transistor M1, which behaves as an amplifier. This transistor is biased at the gate with V biased, and we have the input is applied at the source, where at the source we have VI connected to RS, and over here we have the source capacitance, we're going to call it CS, and the output is connected at the drain, where we have VDD connected to RD connected to the drain, and there's an equivalent capacitance at the drain, we call it CD. Keep in mind that CD and CS here are the parasitic equivalent capacitances at the drain and at the source. So what we are saying is there is an equivalent capacitance will go from the drain to ground. This is basically the parallel combination of CDB and CGD, the gate to drain capacitance and the drain to body capacitance. They will behave as they are in parallel, and they will have the equivalent capacitance. The same thing with the source capacitance. It will be the equivalent capacitance of CGS, and if the body is not connected to the source, then it will also be the source to body capacitance. We can draw the small signal model for this particular circuit. So if we use the pi model, we know that the gate is grounded, and then at the source we will have VI connected to RS, and over here we have the capacitance CS, and then we have the current source with GM VGS, and then there is RO across it, and at the drain we have CD connected in parallel with the output resistance RD. What we will do is we will show you the gain of the circuit right away, but you can come up with the gain using any of the circuit analysis techniques that we have. You can apply nodal equations at Vout and at the source at Vs, and you will be able to obtain the gain. But to save some time, and also because we assume that we are good in algebra, we will skip this step and we will move to the gain right away. To simplify the analysis, for simplicity, we will assume that RO is open circuit. Basically, we ignore the lambda effect, and we're saying that the channel modulation effect, or lambda, is equal to 0. Then the transfer function is given as follows. This is the gain as a function of S. V out over V in as a function of S will equal to Gm plus GmB. Keep in mind that we included the body effect here, divided by 1 plus Gm plus GmB times Rs times 1 over 1 plus Cs over Gm plus GmB plus Rs inverse times S. So this is the first pole in the circuit, and then also multiplied by 1 plus S times Rd times Cd. Basically, we have two poles. One pole occurs at the input, caused by Cs. Another pole occurs at the output, which is caused by Cd. Usually the output pole is dominating in the common gate amplifier, and the reason is Rd usually is much large and Cd is much bigger than Cs, and that means the output pole is the dominating pole and it occurs at lower frequency. Also, if you would evaluate the input impedance, just to save us time, we will only give you the equation, but you can verify it using a test voltage and the test current method. Then we can say that Z of D will equal to R of D in parallel with 1 over S times CD over Gm plus GmB times Ro plus 1 over Gm plus GmB. So basically what we're saying here is the common gate amplifier is also a function of frequency. Its input impedance is a function of frequency, and you can calculate the output impedance as well, and it will be a function of frequency, and the gain, as we said, is also a function of frequency. The next amplifier we are interested in is also the Cascode amplifier. Remember, the Cascode amplifier uses two transistors as amplifier transistors. One transistor gives you a large current gain, while the second transistor gives you a large voltage gain. So let's look at a simple Cascode amplifier. So what we have here is we have an input voltage connected to Rs, and Rs is connected to the first transistor M1. M1 is the current amplifier, which is connected in Cascode to a second amplifier we call M2, and M2 will give us a large voltage gain. Now, the output of this amplifier is simplified here with RD, but we know that you can use diode connected or biased transistors, and it can be also cascoded transistors instead of RD. But for simplicity, in this particular example, we're showing you RD is connected to the output as a load, and then RD is connected to VDD. Each transistor, as we said, has three dominating capacitances. For transistor 1, we have CGS, which is connected from the gate to the source, and CGD1, which is connected from the gate to the drain, and we have two, watch out here, we have two capacitors connected from the drain to ground. We have CDB1 because the body always grounded, and then we also have CSB2 because there is a capacitance from the source to the body always ground. Remember that the body is always the lower voltage in the circuit for the NMOS transistor, right? So from the source of M2 to ground there's another capacitor, so we have two capacitances over here. The second transistor also have three equivalent capacitances. We have one from the gate to the source, we're going to call it CGS2, and one from the gate to the drain, we're going to call it CGD2, and then there is a capacitance from the load to the body, we're going to call it CDB2, and then another capacitance from the load to ground, we're going to call it CL. So these are the capacitances we have, and you can add any other equivalent capacitances come from RD, because remember RD is a transistor, so if there is equivalent capacitances looking up, they will be added up to CL. But in this particular circuit we don't have it, so we're going to ignore it. Now the Cascode amplifier has three poles. So to find out the poles, what we will do is we will label these three nodes. We're going to label the gate of M1 to be node A, we're going to label the drain of M1, which is the same as the source of M2, to be node X, and then the output we're going to label it node Y. So each particular node has a pole. To find the poles at each node, we have to find the equivalent capacitance at each node and the equivalent resistance at each node. And then we can find the time constant, or we can find the pole, which is 1 over the time constant, at each particular node very easily. So the first thing we have to do is we have to simplify the circuit by simplifying CGD1, because CGD1 experiences the Miller's effect, right? Because it is connected from the gate to the drain of M1, and there is a gain for this transistor. However, the gain from A to X is very small, usually approximately to be 1. We are going to say that the gain is very small, and we're going to say that Vx over Va will equal to minus Gm1 over Gm2 plus Gmb2. Then we can calculate the pole at node A. To calculate the pole at node A, what we have to do is find the equivalent resistance and find the equivalent capacitance. The equivalent resistance at node A is very easy. It's basically Rs, because looking into the transistor there is infinite resistance, and looking on the other side there is only Rs. But we have two capacitances at node A. One is CGS1 and the other one is the Miller effect of CGD1. So what you will have, the pole at node A is located at omega PA will equal to 1 over Rs times the equivalent capacitance, which is CGS1 plus 1 plus Gm1 over Gm2 plus Gmb2. That is the gain of the amplifier times the Miller capacitance, which is CGD1. So that is the pole located at node A. Now, there is another pole located at node X, which means at the drain of M1, or the source of M2. To do that, we have to calculate the equivalent resistance at that node, and we have to calculate the equivalent capacitance at that node. The equivalent resistance at that node can be approximated to be the resistance seen through the source of M2, which is 1 over Gm2 plus Gmb2. That should be in parallel with RO1, but RO1 is very large and Gm2 plus Gmb2 is very small. That means the equivalent resistance is 1 over Gm2 plus Gmb2. So we know the equivalent resistance at node X. Then what we have to do now is we have to calculate the equivalent capacitance at that node. The equivalent capacitance at that node is basically 2 times CGD1. That is the Miller effect at that node, plus CDB1 plus CDB2 plus CSB2. So these are the capacitances looking from the drain to ground, plus the capacitance looking from the gate to the source of M2, which is CGS2, because the gate of M2 is grounded. You know, it's a DC value, it's grounded. Then now the pole at node X will equal to Gm2 plus Gmb2. That is basically 1 over the resistance over 2 times CD1 plus CDB1 plus CSB2 plus CGS2. That is basically the pole at that node. Now finally we are interested on the third pole, which is located at the output. So the pole at the output is given as omega py will equal to, if you will look at the output, we have RD as an output impedance. Since this is an approximation, we're going to say that the output resistance seen at the output is RD, but we know that it's not RD, but we're going to assume it is RD. The output capacitance at the output is basically CDB2 plus CL plus CGD2. And here you go. Now we have the 3 poles. Then the transfer function, the overall transfer function, can be approximated as A of S, which is the gain, will equal to the DC gain or the mid-frequency gain, which is minus Gm1 times 1 plus Gm2 plus Gmb2 times RO2, the whole thing multiplied by RO1, which is in parallel with the top resistance, that is RD. So basically it is Gm1 times the output impedance. Now we're still gonna have the effect of the three poles, and the effect of the three poles will be 1 plus s over omega pa. That's the effect of the pole at node A, plus 1 plus s over omega bx. That is the effect of the pole at node x, plus 1 plus s over omega py. So basically what we are saying is you can approximate the gain of the amplifier using the DC gain or the mid-frequency gain and multiplied by the location of the poles, and you combine it in terms of the transfer function. Keep in mind that this is approximation, and when you implement RD using another two cascoded transistors, this circuit becomes a little bit tedious to calculate using the S domain, and you have to have shortcut approximations. And one of the techniques to do is to look at R equivalent and C equivalent at each node, and this way you get the location of each pole at each node. And that's what we did here, and this technique is a valid approximation, especially in this particular circuit. We would like to study now the frequency response of the differential amplifier. So let's go back to the circuit and redraw the circuit for the differential amplifier. Remember that the differential amplifier has two matching transistors, M1 and M2, which are connected together at the source. And over here at the source we will have biasing transistor to give us the current source. We're going to call it M3, whereas M3 is biased using V biased. The input signals for the differential amplifiers come at the gates of M1 and at the gate of M2, whereas the drain of M1 is connected to RD, which is connected to VDD, and the drain of M2 is also connected to another RD, and that is connected to VDD. Now the output voltage is across the drains of M1 and M2. We have to keep in mind that M1 and M2 are perfectly symmetrical, at least for now, and RD for both transistors are matched. Then we have this perfectly matched condition. Under this condition, we can use the half circuit equivalent circuit. So the differential amplifier has the following equivalent circuit. What we will do is we will say half of the circuit will have M1, and then we're gonna make the source connected to ground, because under perfectly matched condition the biasing transistor has no effect in the circuit. So under this condition, the biasing transistor has no effect in the circuit, and we're going to assume that the source is grounded. This is the way it goes because the other half of the input voltage goes across the second transistor and they are symmetric. So you're going to say that the source is the middle point where it's going to read 0 AC, because it is symmetric between M1 and M2, and half the positive voltage will go across M1 while half the negative voltage, the differential negative voltage, will go across M2. So the source of M1 and M2 will have the zero ground as far as the AC signal. Then we have the input signal, which is coming to the gate of M1, and then we have RD connected to the drain connected to VDD. Now we're going to add capacitors for this transistor. We know that there is a capacitance called CGS, which is from the gate to the source, and then we have another capacitance called CGD, which is from the gate to the drain, and another capacitance which called CDB, which is from the drain to the body, as we've shown you here. It is obvious that the Miller effect on CGD is present. We have it, right? Because you have a gain from the gate to the drain of M1, there is a gain. So what we will say now, we will say this capacitance, the CGD capacitance, will have two capacitances, the Miller capacitances. One Miller capacitance will be at the gate or at the input, and another one will be at the drain or at the output. So the Miller's capacitance at the gate or the input is given as C1 will equal to CGD, that's the capacitance itself, times 1 plus the gain, which is GM times RD in parallel with RO. Remember, Miller theorem says 1 minus the gain, but the gain is negative, so 1 minus the minus becomes a plus, right? So this is the equivalent Miller capacitance of CGD at the input. Now there is a similar capacitance at the output, and this is the Miller capacitance at the drain or at the output, where we will say C2 will equal to CGD, which is the gate to drain capacitance, times 1 plus 1 over the gain GM times RD in parallel with RO. And that is approximately CGD, because the gain usually is larger than 1. Then we will say that, then we say C2 is approximately the capacitance itself. So that is interesting as well. So what we end up with is we end up with the poles are the same as the common source amplifier. And keep in mind that for the differential amplifier, what do we do when we use the half circuit symmetry? We say that this occurs for the first voltage, and the other circuit, which is identical to this one, will occur for the second input, right? Because there is two inputs, one at each end. Then you add up the two gains to give you the output voltage, which means that you will have the same response only added, right? So basically, using the Miller approximation, what we end up with the equivalent gain, or the mid-frequency gain, or if you want to call it the DC gain, and we have two poles. One pole is due to the RC circuit at the input, while the other pole is due to the other RC circuit at the output. So we have two poles. Then we can say that the overall gain will look as the common source amplifier. Then we say that the differential gain A of S, which is V out over the differential voltage, that is V2 minus V1, will equal to minus GM times RO in parallel with RD. This is basically the mid-frequency gain, or the DC gain, divided by the effect of the two poles, and the first pole is 1 plus S over omega P1, and the second pole is 1 plus S over omega P2, where omega P1 is basically 1 over R1 times CI, and omega P2 is basically 1 over RO times CO, where CI, the input capacitance, is C1, that is the Miller capacitance at the input, plus CGS, which is the capacitance from the gate to the source, and C out is basically C2, which is the Miller capacitance at the output, plus CDB, which is the capacitance from the drain to the body. So basically, the frequency response of the differential amplifier under perfectly matched condition is very similar to the common source amplifier. You're going to have a second order transfer function with two poles, one caused by the Miller effect at the input and the other one caused by the Miller effect at the output. Now, very interesting for us is we would like to see what happens to the common mode frequency response. Remember that what we said is the common mode says that the two inputs of the differential amplifier have the same voltage, or as the signal change at the input, you'll experience that at the output because the circuit is not perfectly matched. So let's look at the circuit first. So what you will have is here is M1 and here is M2 connected at the source together, and also the inputs are connected together to a common mode voltage. And now we're going to replace the biasing circuit at the source with its equivalent AC circuit, which is RO3, and then we have RDs going to VDD for both transistors M1 and M2. Now we're going to add capacitances at the circuit, or here we will include the capacitance of M3 and we're going to call it CP. So it's the capacitance from the source to ground. And we will include the output capacitances, we're going to call them CL, which are the capacitances at the load. So I'm going to give you the gain right away. When you do the analysis, we will say that the common mode gain is given as, remember what we said about the common mode gain, it becomes to delta GM times the impedance of the top over the sum of GMs times the impedance of the bottom plus 1. So what we have is the top will be delta GM, that's the mismatch in the transconductance between M1 and M2, times RD in parallel with 1 over SCL. So this is basically the mismatch in the transconductance times the top impedance over the sum of the transconductances, which is GM1 plus GM2, times the bottom impedance, which is RO3 in parallel with 1 over S times CP plus 1. So what's interesting here now is not only the gain is a function of frequency for the differential amplifier, it is also the common mode gain, and that is interesting. The common mode gain is a function of frequency, which means that we will have a different response for the common mode gain, and the differential gain is a function of frequency as well. So keep in mind that what we're doing here is we're looking at approximations to understand the behavior of the circuit, but to get the exact or more accurate results, you have to use computer simulations. We're going to stress this all the way through because I wanted you to know that in analog design, you're going to use your intuition to design the circuit, you're going to rely on the computer simulation, and you're going to use your expertise to fabricate the chip on the wafer. As technology changes, the steps required from the computer simulation to the wafer is something that you have to keep learning on the job. Our last circuit in this lecture is the single-ended differential amplifier with active load. So we are interested in the frequency response for the single-ended differential amplifier with active load. Recall that the amplifier has M1 and M2 as the differential input transistors, and they are connected together as a source, and the source here is biased using a current source. We call it ISS. Keep in mind that this current source can be biased using a transistor, but for simplicity we're going to assume that it is an ideal current source, and then the gates of M1 and M2 connected to the differential input voltage, and then we have the loads or the diode connected active current source with M3 is diode connected, and M4 is the mirror transistor of M3, and then we have the load capacitance at the output. Keep in mind that assume CL is large in value and it is part of the load. Now this circuit has two paths from the input to the output. There is a path will go through M1 to M3, which reflects to M4 and sends current to the output, and there's another path that will go from M2 and will send the current to the output, as we discussed in the previous lecture. So there is two paths for the signal to go from the input to the output. So as a result, there is a mirror pole at node E caused by CE, which means that there is a capacitance at the gate of M3 and M4. This capacitance causes a pole for the overall gain of this amplifier, because there is a path will flow through this node from the input to the output. So if we assume RO3 is much bigger than 1 over GM3, and if we Thevenize the two transistors M1 and M2, then the circuit can be approximated to look like this. We will have the voltage source Vx, that is the Thevenin voltage of M1 and M2, connected in series with the Thevenin resistance Rx, which is connected to M3. M3 will have the equivalent circuit of 1 over GM3. Keep in mind that this is the AC signal, right? We are looking at the AC circuit here. And the reason it is 1 over GM3 is 1 over GM3 is much smaller than RO3. So it should be in parallel with RO3, but for simplicity we are ignoring RO3. At the gate of M3 we have the capacitance CE connected to ground, which is connected to the gate of M4, and M4 and the voltage source connected together to the output, and at the output we have RO and we have CL. Now remember that when we did the Thevenin equivalent for the transistors M1 and M2 in last lecture, we said that the Thevenin voltage Vx will equal to Gm2 times RO1 times Vi, and Rx will equal to 2 times RO1. Actually it is RO1 plus RO2, but because the two transistors are identical, M1 and M2 are identical, then we say that Rx will equal to 2 times RO1. So now we can find VE, which is the voltage at the gate or across the capacitor CE, very easily using the voltage divider. Basically what we do, we say that VE will equal to Vout minus Vx times the voltage divider, which is the impedance at the load, which is 1 over SCE plus GM3 over 1 over SCE plus GM3 plus Rx. Note that 1 over GM3 is in parallel with the capacitance CE, right? Because VDD is grounded as far as the small signal is concerned, so the 1 over GM is in parallel with the CE capacitance. And if you look in terms of the admittance, parallel admittance are added up, so that's why you see the GM3 plus SCE, because they are in parallel, they are added up. Then if you take the inverse of that resultant admittance, that is the impedance, the resultant impedance, right? And then you just use a voltage divider. You say the voltage across the capacitor is basically the overall voltage, which is Vout minus Vx, because VDD is ground, right? So these are all the AC voltages. And then you say the voltage across the capacitor, which is the same as the voltage across the GM3. So that will equal to the same impedance, which is 1 over SCE plus GM3 over the sum of all these impedances, which is the 1 over SCE3 plus GM3 plus Rx. Right? So it's nothing but a simple voltage divider over here. Note that the small voltage VE causes the current through M4. So the small signal voltage VE causes the small signal current through M4. We can say that I4 will equal to minus GM4 times VE. Also, we know that Ix, which is the current flowing through the Thevenin equivalent circuit, can be expressed as Vout minus Vx minus Ve over Rx. And then we can apply KCL at the output, so we can say that Ix plus Ve times Gm4, which is the current coming from M4, plus the current flowing to the output, which is Vout over 1 over SCL plus RO4 equals 0. This is by KCL at the output or at the load. And then after some algebra, we can come up with the overall gain. Vout over Vi will equal to Gm1 times RO1 times 2 times Gm4 plus S times CE over 2 times RO2 times RO4 times CE times CL times S squared plus 2 times RO2 plus RO4 times CE plus 2 times RO4 times 1 plus 2 times GM4 times RO1 times CL times S plus 2 times GM4 times RO4 plus RO1. So this long gain expression can be simplified into the following. We can say that Vout over Vi will equal to A0 times 1 plus S over omega Z1 over 1 plus S over omega P1 times 1 plus S over omega P2. Basically, from the transfer function, we know that we have a 0 and we have 2 poles because we have a second order polynomial in the denominator. Then we can find the first pole, which is the dominating pole, omega P1, to approximately equal to 2 times Gm4 times RO4 plus RO2 over 2 times RO2 plus RO4 times CE plus RO4 times 1 plus 2 times GM4 times RO4 quantity multiplied by CL. Basically, if we assume that 2GM4 RO2 is much bigger than 1, and we can say that omega P1 approximately will equal to 1 over the parallel resistance of RO2 in parallel with RO4 times CL. And we can also see that omega P2, which is the second pole, that will equal to GM4 over CE, and the 0 omega Z1 approximately will equal to 2 times GM4 over CE. Finally, the gain A0 is given as GM2 times RO4 in parallel with RO2. So far we have described the frequency response of different topologies and different amplifiers. We used the Miller theorem approximation, and sometimes we derived the transfer function from scratch by drawing the small signal model, and sometimes by finding equivalent resistance across each capacitor in the circuit we were able to obtain the location of the poles and the zeros, and we were able to approximate the transfer function. So the amplifiers usually do not amplify high frequency signals, and usually the gain dies at high frequencies. So part of the challenge or the trade-off also is how could we increase the bandwidth of the amplifiers, right? So you have to go back and you have to minimize the capacitances and the resistances, and by minimizing the resistances you end up with lower gain, so the gain and the bandwidth is a trade-off.